Hi, my name is Johannes Herrmann from the Department of Physics, ETH Zurich, and today we will learn about how to use tunable ZZ interactions to implement a conditional phase gate. What we already can see on the title slide is actually the core portion of our chip, where we have our two qubits marked here in blue and in red, and the third frequency tunable element, our coupler, which we will make use of to implement our gate. So how are conditional phase gates typically implemented? Typically, we will make use of the resonant exchange interactions with a non-computational state, here the 2-0 level, to implement a conditional phase. And this is either activated by tuning disassociated energy levels directly into resonance, or by parametrically modulating at the correct frequency. Since this mechanism involves interactions with a non-computational state, this type of gate is prone to have leakage errors. So what we will show here is an alternative approach which uses the tunable ZZ interactions between two qubits to implement a conditional phase gate. And how does it work? So if you now look here in a simple picture where we have our two qubits, qubit 1 and qubit 2, which are coupled via this tunable ZZ rate alpha ZZ, and we now excite qubit 1, qubit 2 will slightly be moved out of its rotating frame and collect a phase with the rate alpha ZZ. And if we now can switch on and off these interactions, we can implement a two-qubit gate. And why do we think this is interesting? This mechanism does not involve any interactions with this higher non-computational states, and thus is fully dispersive and will exhibit low leakage. Furthermore, we will show that this mechanism allows us to easily tune up any conditional phase, not only pi. And also this scheme is compatible with fixed frequency qubits, since we only have to tune the frequency of our coupler here to implement our gate. And we will see that we can realize high on-off ratios, since we can tune alpha ZZ from 60 kilohertz to 60 megahertz. That's 3 orders of magnitude. And how did we implement our circuit? So what we can see here again is a photo of the core portion. And the two transmon qubits are here and are both interfaced by this coupler element. If you now only have two qubits coupled via a fixed coupling rate, also the ZZ interactions will be fixed. And in order to make things tunable, we have to add this frequency tunable element here, which makes the effective coupling between the qubits tunable, and also with this, the ZZ coupling strength. And we can look at the device parameters and see that the qubits are roughly parked around 5 gigahertz with a detuning of 400 megahertz, which is larger than the atomicity, and the coupler is parked more than 2 gigahertz above in the idle position of our gate. And the first characterization to set up our gate is we measure the ZZ rate versus the coupler frequency, what we can see here on the left-hand side. And the black dots are actual measurements and overlaid with theory, which agree very well. And if you now look here, this is a log scale, we see that ZZ interaction is tunable over 3 orders of magnitude. When the coupler comes really close to the qubits, ZZ rises rapidly. And for a certain coupler frequency, we have a ZZ coupling of 60 kilohertz. And how do we now implement our gate? So we will park our coupler at exactly this frequency here. Then we will pulse it down to the qubits and then activate a ZZ interaction between them. And then we will sweep our time tau and measure the conditional phase and then tune up the desired phase angle. And this we can see here on the right hand side, where we sweep the pulse length and record the conditional phase, and we can see a nicely linear dependence. That's also what we would expect. And since now the conditional phase only depends on a single parameter, the tune-up of such a gate is rather simple. So how does it work? So first we fix the flux pulse amplitude, and then since the conditional phase now only depends on this one free pulse parameter, the pulse length, we can sweep this one and record conditional phases for different pulse lengths. And now we can, since this is a nicely linear behavior, just do a linear fit of these conditional phases versus the pulse length and interpolate any target conditional phase angle by looking at this line. We can repeat the same tune-up procedure for the dynamical phase, and then we are ready to benchmark our gate. And since we are now interested in not only how the gate performs in a quantum computing application, We also want to benchmark different phase angles, since we're interested in how it would perform in a variational quantum algorithm where it is beneficial to can realize arbitrary angles. So first we start with an angle of pi, where we do a quantum process tomography and see a fidelity of 98.8%. Then we repeat this procedure for more angles and cover a range of 2 pi, such that we can realize a VQA algorithm. And we see process fidelities ranging from 97.6 to 98.8%. And in total, we can realize an average gate length of 65 nanoseconds. And now, to further optimize our gate, we want to make it as short as possible. And we will now focus on a quantum computing application where we want to implement a C0 gate, and thus we implement a conditional phase of pi. And now we see here on this plot that the pulse length versus the conditional phase for different pulse amplitudes. And if you have a different pulse amplitude, it means you have an effective higher ZZ coupling rate during your gate. And so the slope of this line is purely determined by the alpha ZZ in this regime. And now we can see that by increasing the amplitude of the pulse, we can easily increase the speed of our gate. But what is us limiting here? Then we have to look at leakage of our gate. And leakage in our system is not as simple as if you have just a 2-qubit system. We also have to look at possible coupler states. And so when we label leakage here, we mean that leakage is the sum of the states. First, the qubit subspace, where we have the F, GG and GFG levels, but also it could be, it's possible that we see from numerical simulations that the population from the qubit 1, which is high in frequency, swaps into the coupler during the gate. So we also have to monitor this channel. And how does it work? So in principle, our coupler also has a small dispersive shift on our readout circuitry, and thus we can also classify this scenario here. And if you now look at the plot here, we can see a sweep of the pulse length and the recorded leakage sum here. And we see that after a certain threshold amplitude, we see that leakage occurs. And so if you now think about what frequency of the coupler this corresponds to, this scenario where leakage starts to matter, it's when the coupler comes relatively close to qubit 1, and the tuning is just 200 megahertz here, and then we see that it starts rising. So we see that our gate speed is mainly limited just by the pulse amplitude and by leakage here. And to go for further benchmarking, we now choose a conservative choice where we have low leakage and the conditional phase of pi, and this corresponds to a pulse length of 38 nanoseconds. And now, in order to get a precise number on the gate fidelity and on the gate leakage, we do interleaved randomized benchmarking, where we interleave our gate in a random sequence of Cliffords, and then by comparing both depolarization rates of the RB and IRB, we can extract a precise measure of the fidelity, which is, in this case, for the 38 nanosecond gate, 97.9%. And we further can also estimate the coherence limit here by interleaving an idle gate. That's just a gate which is doing nothing but has the same length as our gate. And we see that this is a little bit higher, the coherence limit, about 99.4%. But interestingly, we also now can extract from the RB leakage rates. And this we do again by comparing the RB versus the IRB. And then we see that we have leakage on the subpyramidal level. Here we see that we have 0.07%. And this is again not only leakage into the qubit subspace, but also into the coupler. So with this, I would like to conclude my talk. And so what did we do? So we did the first demonstration of a ZZ coupling-based 2-qubit gate. We achieved a fast 38 nanosecond gate with a fidelity of 97.9%. We demonstrated low leakage in the system on the subpyramidal level, which is important if you think about an application in today's error correction codes, then they only can deal with errors in the qubit subspace. We also showed a way how to directly implement a conditional variable phase gate where we can vary this angle, which is important for applications where we need this type of gate, for example, in a variational quantum algorithm, such that we can have a more efficient implementation there. And last but not least, since this mechanism is now purely dispersive, one could think about really parallelizing the execution of 2-qubit gates. That means like doing them simultaneously, which can help you to reduce the runtime of certain algorithms. Thank you for your attention.